Oh, okay, recording. So, whew, um, today I want to. Oh, you know what? Let me. Well, first of all, am I sharing my screen? I don't even know. This thing. I'm sorry. Every time I share my screen, the something else happens. Well, I'll pull something up a little bit later. It's just it's a reminder. I know that I think in this let me pause. There's no reason to talk about this. Pause. Chapter 6. Actually, no. I want to get back to the question I had. And it was a great question. It's actually the timing is really good too, because we've started to talk about attenuation coefficient. So every centimeter of travel, there is a certain amount of attenuation, and that doesn't change, assuming the tissue is the same. Let's say it's every centimeter of liver, the attenuation coefficient is the same. Well, actually, no, I should say the attenuation coefficient will be the same no matter what, because it's found simply by, let's write this down. Let's write this down so I'm not just, it's basically frequency divided by 2, right? So whatever your frequency is, divide that by 2. And then the answer is in decibels per centimeter. That is not showing up very well, is it? And so that occurs no matter what. We have this attenuation coefficient. And it does change. So this is really, how about this? Average. Just like there is an average speed of sound. You know, it's actually not 1450 meters per second all the time. It does speed up, slow down, depending on the tissue. Well, the attenuation coefficient changes depending on the tissue. So frequency divided by 2 is an average. So the question, dang it, I'm sorry, this is a rough, this is a rough day or, all right, never mind. I'm not going to, I should have spent the time finding the question earlier. The question is basically relating to the incident and reflected intensities and the phenomenon of through transmission or posterior enhancement. Those are two words, two things mean really, they really mean the same thing. And we've also learned about our TGCs. TGCs. Now, when we see our TGCs, they could be set up so they're straight up and down. They can be set up so they're swept. By the way, sometimes it's called swept gain. And so when I sweep the TGCs like this, what I'm telling the machine to do is to listen harder down here, and up top, we don't have to listen quite as hard. Well, that kind of makes sense. It's, you know, far away, listen harder, but sometimes we sweep it the other way. Let's use a different color. Sometimes we might even sweep it this way. so that you listen less. That's usually it's the other way around, but sometimes what we don't see, what we'll never see, is the built-in TGCs. Now, actually, one of you were asking me today, what is the difference between the different presets? And I couldn't think of a lot of things at the time. And actually, built-in TGCs is one of the differences. So the invisible TGC, that'll be my invisible box, might be, well, it's definitely going to be swept from upper left to lower right. So it might be steady for a while and then swept and then maybe steady again, creating a line of hidden TGCs, built-in TGCs that are like this. And what does this mean? It means that the machine, no matter what, is going to listen less hard here than it listens to here. And I'll say this is a liver exam. And we set the exam for abdomen, or we set the exam for right upper quadrant. The engineers kind of figured out what the standard attenuation is. Well, they use this equation, and then they tweaked it because this equation's not perfect. So they tweaked it, and this is their tweak. They said, well, we're gonna say, yeah, it works fine. F/2 works fine, and then it's gonna be kind of a little bit. We're gonna listen harder here, and then in the far field, we find that for whatever reason, it's okay down here, so we're gonna continue straight down from there. Or we're not gonna continue to listen harder. We're gonna listen at the same rate over here. So that's a built-in and invisible to us. We'll never see it. When we do our TGCs, what we're simply doing is saying, no, this isn't working for me. We're going to come down like this, and we're going to do that. So that's us. We do that. We've basically said we're going to tweak your standard TGC. This is a really long answer to what you thought was a simple question, but it's not a simple question at all. It's actually a very complex question. Okay, so we have a built-in hidden TGC. We have TGCs that we can change. What does that all mean? That means that the machine assumes a certain amount of attenuation. It's assuming that amount of attenuation per centimeter. Not to mention the engineers already went in there and they kind of they tweaked it. So you got that to the pile. But then we run into assist. So let me create, oh, I know how to do this. This is perfect. That's not how you do it. Let's try this instead. Okay. This is going to be liver tissue. Now, just like over here, as sound travels, it's going in Oof. Just too much. Sound's coming in. It's bouncing back. It's going in. It's bouncing back. Actually, let's make these first ones a little bigger. And then so I don't know how clear that is. Basically, we have our that's the incident sound beam going in, and then all the echoes coming out. This happens as this goes along. They get weaker and weaker and weaker. The beam gets weaker because of attenuation, reflection, scattering, and absorption. The echoes get weaker because the beam is weaker. And of course, not only are the echoes weaker, but the echoes still, they have to make that travel too. So they're being attenuated on the way back. So the echoes have a double whammy. They get attenuated when they start, and they get attenuated all the way back up. So we assume this normal attenuation. We have our gain swept like that. And so basically the machine automatically listens harder down here. So in order to create a smooth image from top to bottom, and not one that goes from bright to very dark, the machine, every microsecond of time that passes, which is the same thing as saying every few millimeters of depth, every microsecond of time that passes, it listens harder. Another microsecond passes, it listens harder. Another microsecond passes, it listens harder. And it keeps doing that in order to create a steady or a consistent screen. Now, we come in and create a cyst. Okay, my attenuation coefficient was frequency over 2. Let's say it was let's say it was right there at the half. So 3 decibels per centimeter, decibels, and then 3 decibels per centimeter. 3 decibels per centimeter, and then it gets to the cyst. I should probably make this a little more clear, huh? So every centimeter that's going by, it's a negative 3 dB, negative 3 dB, negative 3 dB. And then we get to the cyst, and let's say there's 2 centimeters, and then we're down here. Well, actually, let me start right down here again. Negative 3 dB, negative 3 dB. So the tissue is acting as expected. Every centimeter that goes by, we're losing half the energy, half the intensity of the beam, 3 decibels. We get to the cyst. Well, let's go with the extreme example. And it's actually not far from this. 0 dB, 0 dB. Here we are. We've made all these assumptions. We're assuming that it's all just liver. The machine is. We know better, but the machine has to make assumptions. It's assuming an attenuation coefficient of frequency divided by 2 In this case, that attenuation coefficient happened to land perfectly at 3 dB because it's what I wanted it to be, which means half of the energy is lost every single centimeter. And so, and then the engineers built this invisible time gain compensation, TGC, and it's now wrong. It's wrong right here in this area. Ugh, I feel like I'm not zoom in a little bit. Help. Okay. So in that area, it's wrong. So that assumed 3 decibel loss does not happen. If it does not happen, that means that all this stuff back here, let's do bright yellow. Oh, how about this? This is my through transmission here. It's extra bright behind the cyst because we assumed 3, 6, 9, 12, 15, whew, okay, can't count by threes very well. It's assumed 15 decibels of attenuation. Do we add it like that? Well, yeah, it's assumed 15 decibels of attenuation, but it only got 3, 6, 9 decibels of attenuation. So when it hears an echo, this is still a weak echo from down here, down at this level, but it's listening so dang hard that it makes it bright. It makes it too bright. It's making a poor assumption because the machine doesn't understand that there's a cyst here in the middle of the field of view with 0 decibels of attenuation. So we assume 15 dB. I'm just going to put a negative 15 dB, but we actually got negative 9 dB, which, by the way, between 9 and 15 is a huge difference. Therefore, machine thinks echoes are stronger. No. So I gotta be so careful. The machine actually doesn't think echoes are stronger. Echoes are stronger because they missed this attenuation. So they are stronger than expected. Machine thinks, that's not what I wanted. Attenuation was constant, and it wasn't. So that is a really long explanation for what you thought was a simple question. None of these questions are simple. Well, some of them are. So that steps ahead a few chapters, but it's an apropos time to talk about this because it really brings in everything we're already talking about. So I went ahead and decided to go for the full explanation. We'll run into this again, but gosh, actually not for not until I think the end of the book. Artifacts, yeah, chapter 21. So we're way ahead of schedule. That's awesome. Okay. Chapter 6. I want to get back to chapter 6. Let's, if you guys don't mind, I'm going to do some big time erasing here because that is not chapter 6. So I will say again, because this is so important to know the difference. Impedance, Z in rails, tells us if and how much reflection there will be at a tissue boundary. And the equation that we started with, Z, IRC, the intensity reflection coefficient, that whole equation really only works at a 90-degree angle. Once we start hitting sound at an oblique angle, impedance still matters, but the equation doesn't work. So this equation is only for this kind of interface here, where we have a tissue 1, tissue 2, impedance 1, impedance 2. There is a reflection, therefore there is an impedance mismatch. If Z1 equals Z2, no reflection, and by the way, invisible. We cannot see it if there's no reflection. If the reflection is small, kind of like what I've drawn here, that means there is a small difference between Z1 and Z2, and that's actually normal in the body. If I drew the reflection to look more like this, that's kind of a visual indication that the reflection is almost as strong as the sound, the initial sound beam. That would be a very large impedance mismatch. Now, impedance, remember, is density of the tissue times the speed of sound in the tissue. So we already know that air is not the same density as tissue, and it's much slower speed of sound. So its impedance is very different. Bone is more dense than soft tissue, and the speed of sound is much higher. That too has a large impedance mismatch. So the ironic thing is that these guys over on the corner, air and bone, which can you see me doing this, air and bone, even though they're completely opposite, they have the same effect on sound. And that is a pretty much reflect everything. So just quickly again, make this pen a little bit, oops, I'm going the wrong way. Make that pen a little bit bigger, I might write better. Okay. Intensity, reflection, coefficient. We're going to do this in percentage. So once again, this is kind of, it's one of those things that you can get a ratio or a percentage. We're going to do percentage here. We did this the other day. Z2 minus Z1. Please tell me I just did that right. Z2 plus Z1 squared is equal to a product times 100 is equal to the IRC. I wonder if we should transmission coefficient. you're basically just, just remember, it's pretty easy to remember if you just think of it this way. There is a incident, there is a reflected, and there is a transmission. If the incident is 100, and we'll just, let's say 100 watts, and the reflected is 25, and the transmitted is 75. In other words, incident is equal to reflected plus transmitted. And we could write this different ways. We could also say, we could say the intensity transmitted coefficient percentage is equal to, so that would be the transmitted divided by the incident. Wait, why would that? Intensity, transmitted intensity divided by, yeah, that makes sense. So the transmitted intensity, so if you want to find the intensity transmission coefficient, ITC, you simply find out what the transmitted energy is, divide it by the incident energy. That'll give you that percentage, which would, in this case, would be just simply 75%. Okay, I want to stick to concepts. I was also thinking we probably need to do, and I don't have time, but when I do have time, I don't have time in class, to sit here and work out equations, but you know what just occurred to me? I'm going to do that on my own time and publish it. And so if you guys have trouble kind of figuring out how to do these questions, let me do that. And you guys could you could even suggest specific, in fact, perfect. Suggest specific questions you're having trouble with in the book, or just questions in general. Let me know about that, and I'll put it into a review. Because it's better, it's easier and better for me to spend my time on concepts, and then if we need to work out the math, we'll do that separately. The reason I say this is because I really want to get into the other big concept here, and that is the fact that I'm writing too large. Okay. Okay, the other big concept, we talked about this already, but is refraction. So that has everything to do with speed of sound, or speed of light, as it were. So I'm going to draw in our normal, almost normal. Use a different color, and I'm going to come in at an angle here. So an incident sound beam comes at an angle. We talked about the other day how that can then, it could change directions from, can go farther from the normal. Remember, this is the normal down here, the green line. So in this case, let's just draw, I'm going to go ahead and draw some angles in. If we draw theta I for incident, It's like a one-eyed man frowning. Anyway, theta I, and we now have a theta T, which is obviously larger, right? This angle down here is larger than the angle up there. Both of them measured from the normal. My mnemonic for this is speed up. In other words, tissue 2 sound, whoops, is greater. Kurt's rule is that every percentage, for like a 1% change in the speed of sound, creates a 1% change in the theta transmitted angle. And that could be up or down. So using a different color, if I'm now down here, and my theta angle is now this tiny little guy, theta T, that is slow down. Now, if I'm Edelman, I draw this entire picture on its side. I think I know why he does that, because of the normal. He's using the normal as the horizontal. I get it. I don't agree with it, but I get it. The reason I don't agree with it is because we scan most of the time with our hand, from top down, and it just seems more natural for me. So what I was going to say is, if he writes this and draws this sideways, speed up and slow down still apply, but they only apply to the actual theta angles. So slow down, the angle went down, the size of the angle went down. Speed up, the size of the transmitted angle went up. That always works, no matter how you draw this. It just gets a little funny is sometimes if you draw it sideways, because we also think of, right, speed up, right? Yeah, that's sped up, and this is sped or slowed down. Well, when you draw it this way, it works in that way too. If you draw it sideways, it might not work that way. I just want you to be careful about that. So the mnemonic always works with the actual values, not with the pictures, I guess what I'm trying to say. Oh, by the way, so what's the refraction angle? Let's say the speed in tissue 2 is 25% greater than in tissue 1, and we have a good color here. Let's use red. And I'm coming straight down like so, and that's my sound beam. I have a speed of sound. C1 is and then C2 down here. Tissue 1, tissue 2. Speed of sound in 1, speed of sound in 2. Speed of sound in 2 is 25% greater, right? Now, if I say Kurt's rule, or also the sign Snell's law. Snell's an idiot, though. Just listen to me. Kurt's rule says for every 1%, there's a 1% change in transmitted angle. So a 25%, that would make a 25% change in angle, right? So this red line is coming straight down. Where does it speed up, slow down? What does it do? What do you guys think it does? Right. It does nothing. Refraction only occurs when there is an angle involved. If there's no angle involved, the sound will continue on straight. One of the things, I know it's El Paso and we're in the middle of the desert, but if you've ever been on a dock with fish, or, you know, I know I'm being smart ass here, but as you're walking up to a body of water, and it's really clear and you can actually see the fish, I think most of you guys understand that where you see the fish isn't exactly where the fish is. There's a refraction going on, just like this blue line coming in. Oops. Just like that blue line coming in, it refracts. Let's see. It in water, speed of light slows down. So let's see. In that case, the fish. Whoops. Oh, let's get rid of some of this stuff anyway. Speed of light slows down. The fish is here, and the light beam has refracted right towards it, and then the reflection goes back in the same way. Yeah?
Would it be easier to visualize this if we were talking about a straw in a glass of water?
It might be. No, well, yeah, there's actually a picture in your book with a pencil and a glass of water. Does the same thing. But I miss the water, so. So we have our fish down here. The light's coming in, it's refracted in the water, it slows down in the water, it sees it bounces off the fish and goes back. We don't realize that. We're just like the dumb ultrasound machine. What we see or what we think we see is here. This is actually important to note because sometimes in ultrasound we do have some decent refraction artifacts and things are not where they're supposed to be. Actually, some of the artifacts are pretty cool, and invariably we'll be able to see a couple of them in lab. So, real, fake. And that's right. I was going to bring that further on. So as you're coming in, you see that fish, and so if you're bow, I don't know why, if you're bow hunting fish, because that's what you do, where I'm from, and if you shoot right at the fish, you'll miss it. Your arrow is going to go there, and you're going to hit nothing because it's a fake fish. So you have to learn that you aim below the fish, you aim down low in order to get that fish. Now, however, if you come off on that deck, and this is why I'm not using the straw, if you walk onto that deck and you look straight down, now there is no refraction. Because when there's no angle, there's no refraction. And so when you look down, and you see a fish, that's where the fish is. So then in that case, you aim straight down on it and you'll hit the fish. I like it. Snell's law just is what it is. I mean, it literally says, you know, the concepts are beyond the scope of the book. Why mention it then? Oh, that's right. I did want to do a I don't know if I want to get into chapter 7 just yet. There's actually, you know what, let me just look it up. God, could I have any more things open here? You guys can see my screen, right? That I'm hunting on the internet right now.
Yes.
Okay. Oh, I thought that was the GIF. I'm not used to Bing. Okay, so yeah, you know what? I probably picked about the worst one, but I'll pick another one. But this is good enough for now. So this just kind of shows you how this happens. And it's not terribly important that you know this, but this is a situation where the speed of sound, or the speed of light for that matter, is slowing down. So the red lines represent sound waves, each cycle. So perhaps the red lines represent the peak of each cycle. And then the white in between would represent the trough. As the speed of sound, remember when I said the speed of sound will change your frequency? No, I'm sorry. It will not change your frequency. Careful, Kurt. It will change your wavelength. You can see that these waves in the white area, we'll call that air, are farther apart than they are in the blue area. In the blue area, they're a little bit closer together. So the speed of sound has slowed down, and even though the frequency is the same, the wavelength has changed. And so at the boundary, what's happening is that by changing the wavelength and changing the speed of sound, it's slowing down in the blue, but it's still going fast over here. Can I draw on this? I love it when it says GIF and it's not a GIF. Or perhaps it's too slow. I do like this one a little better simply because it's faster. As over here by the, I don't know if you can barely see my cursor here, over by the R and water, you could see things start to slow down. Whereas over on the other end, the velocity of, well, in this case, I assume it's going to be light, but light or sound, it doesn't matter. The velocity is faster. So as it slows down over here, it's going to have to bend down in order for the, how do I say that? It bends downward because it's slowing down and the rest of the beam is still going fast until 100% of the beam is in the water, then it's all going in the same direction. It's actually easier to explain on a board. Okay, it's only 11 o'clock. You know what? We're just gonna squeeze in the chapter 7 a bit because we've already actually talked about it in a way. So this is actually nothing terribly new. I'll just use the same. That was not helpful. I'm just going to use the same thing. Just go off in the corner here. Chapter 7. range equation. So awesome. Yeah, I'm glad we're doing this. We've already talked about this. We've talked about finding range by seeing the light from a lightning bolt and counting the amount of seconds that go by before you hear the thunder. And we've talked about how that doesn't work when there's many lightning bolts and constant rumbling thunder. You don't know which lightning goes to which rumble of the thunder. So we use pulses. Each pulse is a range finder. Our machine is really a range finding machine. Range is done by time. In other words, lightning bolt, 1 second, 2 second, 3 second, thunder, oh, it's 3 miles away. And speed, really. So if you know your velocities and yeah, I'm sorry. If you know your velocity, your speed of sound, and the time it takes for this to happen, for occurrence to happen, you know how far away it is. Now, unlike a thunderstorm, we produce the sound and we receive the sound. So our range equation is more like a submarine. Spaceballs reference, no one needs that, but we produce the sound, we listen for the echoes. There's actually, the submarines also have passive, oh, but no, passive though, you can't do a rangefinder with passive. So a submarine, a dolphin, a bat, an ultrasound technologist, we're all using the range equation, whether we know it or not. So we find that the range equation is depth in millimeters, sometimes called length or path length. We'll stick with depth, so because depth is really what we're reporting to our doctors is depth. Like I found an artery at 2 centimeters deep. Doctor, you might want to avoid that with your needle. Oh, okay, thank you. So, and then 1.54. We're not using 150. We're not doing meters. We're doing millimeters. So 1.54 millimeters per microsecond times the go return time. The go return time. Pulse, echo. That's what they mean by go return time. We're just going to say T in microseconds. Now, we're not interested in the total path length, right? We're not interested in how long, how deep it, or the total path length down to the echo, or from the transducer to the object, from the object back. We're only interested in one of those lengths, really, right? So that's why we divide by 2. Storm clouds, lightning, and thunder, we don't divide by 2. Here we do. Another way of writing this, by the way, I'm just going to put or. Oh. Yeah.
Oh, as you say that when it comes to storm clouds, lightning, and thunder, we don't do the divisible by 2. Is that because we are now the receiver in that scenario? Because the thunder and lightning happen with the clouds, that's what's producing it. And so we're essentially what's being imaged to say?
Yeah, we're the ones being imaged in a way. So it's in the thundercloud analogy, it's only one-way travel. Lightning, thunder. And it's all coming from the cloud to you. In what we do is two-way. We produce it, it bounces off, and goes all the way back. Oh, of course, Doppler radar too. I was mentioning dolphins, bats, Mariah Carey. Time. So remember, that's another way of saying multiplication there. It's just a dot. C, why C? Well, C is 1.54. Speed of sound is 1.54. So that's just another way of writing it. And we don't have to have a 2 in the denominator. We could just simply multiply 1/2 times the product of C, the speed of sound, times the time. So that's just another way of writing the equation. The elapsed time from the pulse creation to the pulse reception is called go return time, or time of flight. The time of flight is directly related to how deep a sound travels. It is. So yeah, that's our entire machine is simply a depth finder. If it takes, well, let's look at the table 7.1 on page 108. If it takes, oh, well, let's just add that in. Here, I'll actually do math. For you guys. It's terrifying for me. My brain will actually, it freezes up when I do math in front of other people, which is 13. So if it takes 13 microseconds, well, let me just do this. Pull my calculator out. Hit clear, 1.54 times 13 equals 19.76. That doesn't seem right. Divide that by 2, 9.88. Close enough. 9.88, which is close enough to 10.0 millimeters. We crossed out the microseconds, they've canceled out. 10 millimeters. We generally in ultrasound don't report things when we don't report depth in millimeters, we report it in centimeters. So 13, you might guess, is an important number for us. This is the 13 microsecond rule. Why 13? Because that's the nearest whole number that gets us really close to 1 centimeter. And so that's the easy number to work with, right? We wouldn't do a 14 microsecond rule because, I don't know, just out of curiosity, what would that be? 1.54 times 14 equals, divided by 2 equals 10. Well, so 13 is closer to 1 centimeter of go return. Remember, that's 13 microseconds is not the time it takes to travel one direction, it's the time it takes to travel 2 directions. So go return time is 13 microseconds. That's the whole number that gets us closest to 1 centimeter. If we did 14, it'd be almost 11 millimeters, in other words, 1.1 centimeters. So anyways, 13 microsecond rule. Why the 13 microsecond rule? Because that's the number that works. So we could add 13 and 13 together and say 26 microseconds And the question is, how far in 26 microseconds? Well, that's going to be 2 centimeters, right? Let's see. Oh, I'm sorry. Oh, yeah. That's stupid. Okay, be careful when you look at this table. I looked at the wrong line. I'm like, wait, why is my number off? The reflector depth is all we really care about. The first row of this table, or the first column, the middle column. 26, 39 microseconds, 52 microseconds, 130 microseconds, and it's just a matter of how many times does 13 go into each one of those. 13 goes into itself once, so that's 1 centimeter. Goes into 26 2 times, so it's 2 centimeters. 39 3 times, so it's 3 centimeters. 52 is 4. And then 130, we've skipped a few. That is 10 centimeters. Well, yeah, 130. 13 times 10 is going to be 130. So yeah, that makes perfect sense. Here, I'll put the 13 up here as well. 13 microseconds, 1 centimeter. Does that make sense so far?
It'll eventually absorb in.
Yeah. I'm looking at a little note here, and this actually reminds me of a question that was asked to me today. Is kind of like how does a machine know everything is back? And well, there's 2 answers to that question. One is right from the book. I know this, blah blah blah. And then there's a little more of a subtle, but wait a minute question part of that. And so this is certainly related. I'm not just going off on a tangent here. I'm going to have to get a little more. 8,000 out of 9,000 will be fine. Well, wasn't as much as I thought it would be. Anyway, how do we know? We have to, the machine, a little transducer here, puts out a pulse. That pulse goes down and down and down. And as it's producing pulses, little echoes are coming back all along the way. So one pulse, remember this is, I'm showing 3 pulses, but really this is 1 pulse just over time. 1 pulse, thousands of echoes. And the question was, how do we know that all the echoes are back? Well, the standard answer is that when we look at our machine, so let me just put, this is our screen, even though I have a transducer on top of our screen. It's kind of a fusion between the transducer and what we see on our screen, if that makes any sense to you. Hopefully it does. We see on our screen a little line on the sides, little hash marks. And let's say, well, we have 10 centimeters. Last one's 10 centimeters. So the standard answer is to how do we know when the next pulse can go out? In other words, our pulse repetition frequency. Well, it takes 130 microseconds for all echoes to be received. It only took a few microseconds here and a few more here and a few more here. But by the time you get to the very bottom of the screen, 130 microseconds have to pass in order for all the echoes to come back. So that's the standard answer, and that's all you really need to know. The problem with that answer, and this is something I've looked up numerous times and I cannot really figure it out, is the fact that you might be scanning to 10 centimeters, but the patient might be 15 centimeters deep. So why aren't we waiting even longer? Because just because your screen ends at 10 centimeters doesn't mean the body ended at 10 centimeters. So theoretically, we should be waiting, let's see, 15 times 13, 195 microseconds. Let's say 200 microseconds. So there's kind of a disconnect there. If you're following me, you know, like there's still more body down here. There's still more tissue. Even though we're not looking at it at all, there's still tissue there. And wouldn't the sound beam continue to travel and echoes continue to come back? So for the umpteenth time, I'm going to try to look that up, spend half my afternoon trying to figure out that answer, because it does not matter. This is completely on me. Does not matter. They'll never ask you that question because they never address the question. So anyway, well, guys, it's 11:20 anyway. I like to be a little more prepared before jumping into pulse repetition and imaging depth. Actually, that is what we're going to be talking about pretty soon. But I do like to be a little more prepared. Oh, chapter 7's. Okay. I take it back. Next time we're talking about chapter 7, and then also I need to work out. I need to look at our test schedule and figure out a test for you guys. We're going to need another test soon. Because transducers is the next chapter. That's chapter 8. That's its own thing, its own test. The subject matter kind of makes a big switch into the theory of sound into the actual hardware, which is transducers. So that's kind of a big difference. All right, next time we meet, we finished 7. I forgot 7 was only 4 pages long. I'm still not prepared for it. I don't want to make a fool of myself. So we'll just finish up 7. We'll do some review. And yeah, perfect. You get another Monday test because I know you guys love the Monday tests so much. And we'll see whether or not I start to whether I start lecture without you guys, just so you guys tell me if that worked, if what I did last Monday worked out for you. But yeah, let me. Sorry. Go ahead.
Are we going to go over our last test like we did?
Yeah. Yes. 11:24. Let me pull up the test. Let me be careful about this, because if I accidentally pull up an individual's test and you see their grades, that's like instantly. I could instantly be fired. Here, you can see my second screen. Okay.
You want to stop recording too?
Yeah, thank you. I don't need to record this.